So we'll continue today talking about this Bose-Einstein condensate that I alluded to at the end of last lecture. And really, what this is sort of an application of boson or Bose-Einstein statistics. Okay, so we'll assume that we have a free gas of bosonic particles, and that free gas of particles follows a distribution. So that's a non-interacting gas. So I'll label the energies, I guess, epsilon. So we have an inverse temperature beta, epsilon k, sorry, that's subscript small, minus mu. And of course, the energy depends on the interactions. But for the purposes of this discussion, we'll just assume that Ek is proportional to k squared. And this would follow, for example, from a non-interacting Hamiltonian in second quantized language. So A dagger A. However, you can just think of it as essentially the kinetic energy. So a non-interacting system, you have a kinetic energy. So 1/2 mv squared, p squared over 2m, with the appropriate quantum modifications on k. Say, for example, if you're a particle in a box or whatever. And what I've included in this distribution is the chemical potential, which is a measure of work required to put a particle in the system or take a particle out of the system. Okay, so hopefully this is something you've seen in your stat mech class. And of course, beta is the inverse temperature, 1/kBT. And what Einstein thought to do was, let's count the total number of particles in a state, okay, using this distribution. So okay, so I'll call that big N. Since our states are labeled by K, that's just the sum of the small n. That's supposed to be an N. Where that density, okay, so I'll write this in terms of N over V. So that we have a density. And just like last time, I'm going to convert a sum to an integral here. And so really this expression for the density is valid, to be maybe more clear than last time, in the limit when, I guess, the volume goes to infinity. Something like that. Okay, and now we can use our trick from last time. So remember, last time we calculated the expectation value, and we argued it's given by this Planck distribution. Now we're just going to sum up the number of particles which exist in a state K. And so in a large volume, we can convert the sum to an integral. And remember, it's V over 2 pi all cubed. So I get rid of that V if I look at the density, which is the only reason to use a density. Just make it look a little nicer. So then this is 1 over e to the b, there's e to the beta, epsilon k, minus beta mu minus 1. Okay, so all I'm doing is writing down an expression for the total number of particles by summing over states, and I'm dividing by the volume. And let's go a few more steps in the same direction that we went last time. So let's consider this integral an integral over a spherical k-space, right? So there's a radius and a radial and an angular component, and we can separate those out by taking the three-dimensional dk into 4 pi k squared dk. And I'm also going to make a variable substitution like we did last time. So in this case, I'll also substitute I'll make a variable substitution so that I have e to the z minus beta mu, the chemical potential there. Okay, so these variable substitutions are basically the way to view these integrals in some sense. Okay, they give you insight into what's going on. So with all these things in place, well, let me skip a few steps maybe. You guys can work it through, see if you get the same expression as me. There's one step, and I'll simplify it down to that expression there. That's dz now. Okay, so I've substituted in, dz is all these constants out, 2k dk, just like last time. And the temperature dependence of this expression falls out in the front here. And, just like before, we can consider this integral. We can imagine taking a lower limit on this integral of 0, either going through the Brouillon zone or extending it to infinity, which is some sort of approximation and so on. But it's not the upper limit on this integral that I'm interested in regard to the Bose-Einstein condensate. It's the lower limit on this integral. Okay? So first off, this is the average number, or sorry, this is the total number or average density of the particles in the system. I want that number to always be positive. My chemical potential is actually constrained. It's highly constrained by that. So now my z is somehow just related to my energy, which is k squared, right? So in the lower limits of this integral, where my z is 0, I have to make sure that I don't have a negative sign coming out here. So first off, there's a constraint on the chemical potential. So mu has to have an upper bound of 0. keep the number of particles positive. Okay, so we're thinking in a grand canonical sense. We're thinking about particles, the particle number in the system that can fluctuate depending on the temperature or the chemical potential, right, in a stat-mech sense. So to simplify things, let's just set that mu equal to 0. Then we're going to solve this integral. And it's similar to what we did last class. Okay, that's just some special function, root z dz e to the z minus 1. And I get all this temperature dependence out in the front. And so my density will be some number which comes from that integral okay, and that actual number out front doesn't really matter, except for the fact that it's, except for its order of magnitude, which will come into play in a minute. And so there's my temperature dependence. It's T to the 3/2. And, what this means is for essentially a given temperature, there's some maximum number of particles that can be accommodated by the Bose-Einstein statistics, right? And that number is just, N max, call it. It's just this density times its volume. So if I give you a temperature, T is whatever, Kelvins, room temperature, whatever. There's some maximum number of particles that I could, squeeze into this system. So think of these experiments. The guys who did this in 1995, they had an optical lattice that they built, like literally from interacting, interfering laser beams, and then they could load, particles. It was rubidium atoms. They could just load these bosonic particles into this cold atom lattice. And so for a given temperature, whatever that temperature is, and for a given chemical potential, which I've just fixed, there's some maximum number of particles that fit into that system. Okay, but now imagine I load a bunch of particles into that lattice and I change the temperature. So maybe this thing's at some moderate temperature. They have some sort of nozzle that sprays these atoms in. Now they're all in their place in the lattice, happy and content, or in the laser trap, whatever it is. And now I can cool this thing down or warm it up. If I fix that particle number and I vary the temperature, at some point that particle number might be more than the maximum amount of particles that can be accommodated in the levels. You know what I mean? So I've just summed up all these levels. There's a maximum number of particles that can be accounted for those levels. And if I cool down too much, that maximum number, which has this temperature dependence, might get less than the number of particles that's actually in my lattice. So for T too low, so for insufficiently low temperatures, if you will, that maximum number of particles that can be accounted for by the distribution is less than n. So what happens to the rest of the particles in this case? So you know where this is leading, because we're talking about Bose-Einstein condensates. But where's the logical inconsistency in this argument? What have I missed when I've taken that integral? It's the ground state. So what happens to the ground state in that? Oh, can you see this? In that integral up there, right, which is counting the number of particles, that integral gives me 0 contribution when my z is 0. Right? So there's no numbers being accounted for the k equals 0 state, or the 0 energy state. And we know that that has to be wrong. Okay? So that's the logical inconsistency, or that's the problem with taking the continuum limit in that integral. We have to make sure we account for the zero energy state. And what happens to the rest of the particles is when you cool down below a certain temperature, they just start piling into that 0 state, that lowest energy state. So quantum mechanically, we know there's one state at k equals 0. And because we're dealing with bosons, we can pile as many particles as we want into this state. That's the statistics of bosons. If we were dealing with fermions, even though we miss the state, it wouldn't really matter, because it only fits like 1 electron, or 2 electrons if you account for the spin. So that's why this is a fundamental property, or fundamental feature of bosonic atoms. So what we should have written for our integral is that integral's fine, but we should account for this 0 energy state. Okay, so whatever that integral is, however I write it over k. I mean, the reason I change variables is it elucidates the fact that z is equal to 0 gives a 0 contribution. Where, I mean, you can see it here because you're Jacobian essentially. But what I should have is also an n naught for the number of particles that can pile into that 0 state. And that's just, again, the limit of, you know, when your volume goes to infinity, it's just like big N. I'll write it. It's big N naught over V. Okay, that's the number of particles in your ground state. And this is called the condensate. That condensate can easily be a macroscopic fraction of your total particles. And as you go to zero temperature, the number of particles in your condensate becomes the number of particles in your system. So it's almost amazing that it took, well, I can't subtract, but 1995 minus 1924 to see a Bose-Einstein condensate in an experiment. And the reason is, like I alluded to, superconductivity and superfluidity, but really in order to see an actual condensate that has the thermodynamic properties that you can calculate from this distribution, you have to have a very clean, sort of non-interacting system that's not coupling to any outside degrees of freedom, like phonons or something like that. And these cold atomic systems, these sort of artificial condensed matter systems, are, they're so isolated that you can essentially make this Bose-Einstein condensate with these rubidium atoms. And I think they've trapped other atoms now. So what was like a big breakthrough, deserving a Nobel Prize in 1995, pretty much any junior faculty member working in cold atoms can now create a BEC in their laboratories. So it doesn't take long for this, didn't take long for this sort of technology, this technological step to propagate. So there's actually a critical temperature for the onset of this condensate. So if I have a whole bunch of particles in the system, I can warm it or cool it, and there's some critical temperature where I get the appearance of this condensate. And I can just figure that temperature out, or an approximation for that temperature, just by inverting this formula, so solving for the temperature. So up in that 2.616. Okay, and it's depends on the number, density. So below that temperature, particles start moving into the lowest energy level. And you can calculate the occupation just by combining these two formulas. So the number of particles in the excited states is just the total number, T over Tc to the 3/2. That's excited. For K labels greater than 0. And the ground state is just N minus this. So the picture you should have in your mind is basically all of these levels. There's a 0 level, so whatever the energy is, or the EK. And these levels have some sort of structure. And for T greater than Tc, well, let's just do 0 less than T less than Tc. Some particles will start to sit in your condensate, in your 0 level. And you'll get a population of particles above, depending on that thermal distribution. is if we're at t equals 0, all of these excited levels drop down into the zero momentum level there. So there's some temperature dependence of the number of particles. So N naught turns on below Tc. So N naught is 0, and then it turns on. Whereas N prime, whatever I called it, picks up the slack. So the total number is N. And this thing here is Tc. So the Bose-Einstein condensate question?
Yeah, I was wondering how universal this is. Say you change the dispersion relation. Would you get the same conclusion? Or do you need...
Well, so changing the dispersion happens through adding interactions. And that does change the physics of the problem. And so actually, you guys will do this in your tutorial today. You're going to take my non-interacting second quantized Hamiltonian and add weak interactions to that. So, and if your interactions get very strong, then you get a superfluid phase. And so the superfluid state, I mean, it has some analogy to the Bose-Einstein condensate, but not everything's the same. So you get actually, so it's, changing the dispersion relation can actually change the physics quite appreciably. But the basic concept of having a whole bunch of, particles collapsing into this lower energy level, it still kind of holds conceptually.
I'm a bit confused about what you mean by N dot. So are we saying above TC there's nobody in the ground state according to the
Right.
picture?
I mean,
Isn't it still the most
you still have some,
place for
you'll still have some, you still have some distribution, so you can have particle numbers fluctuate into that ground state, but it's not a macroscopic number. It's not a macroscopic density somehow.
Shouldn't it somehow contain most of the particles?
No, so I think above TC, most of the particles are in the excited states. Yeah. Like the macroscopic number of particles is in the excited states.
So when we have the sum expression for N,
Yep.
that's just the total number of particles.
Yeah, we're just summing all the particles, but that sum's running over their state label.
So
K.
how then when we changed it to the integral, did it become a maximum number?
So that's a number of particles given a temperature. Okay, so if I have a temperature or a chemical potential, I have a number of states. So I'm really just summing over states, okay? Now imagine I have a fixed number of particles. It's like I have shelves in a room, and I only have so many shelves at a given temperature. But now I give you a whole bunch of books, right? Well, those shelves accommodate all my books, only for temperatures above that T max that I've defined in this way. So I've turned it into like a canonical question now. I have a fixed number of particles. Do I have enough levels to fit those particles in? If I don't have enough excited states, these are my shells. If I don't have enough of these excited states, up to whatever maximum I'm allowed, then the rest of those books have to go into the ground state like this. So I've just taken something that's grand canonical, and I've fixed the parameters, T and mu, and now I've said, this is my number of states. How many particles can I fit in there?
So N counts the number of available states, not the number of...
Yeah, it's a maximum number of particles
Okay.
that can be accommodated. Yeah, so it's the number of states, right? And I could have formulated all this as a density of states, which I don't know if you guys have seen density of states before. Then you're just summing over that density of states to get the total number of states. That's probably a better language for it. So the condensate, so the Bose-Einstein condensate itself has interesting properties. It carries no momentum, right? So, which is totally crazy. So these, I guess, let's say these N naught particles, in this non-interacting k squared case, they carry zero momentum. There's no pressure associated with them, and there's no viscosity associated with them. Because thermodynamically, those quantities are a consequence of having a finite momentum. So some of this translates into the interacting case, like if you have different dispersions. So like the superfluid. So superfluid helium. So for a long time, the only bosonic sort of macroscopic quantum state was helium cooled down to a sufficiently low temperature, where you get a superfluid state. And that superfluid state is essentially detected by its absence of viscosity. It'll flow through, like if you cork a bottle of superfluid helium, the helium just flows right through the cork. It also carries no, it carries no moment of inertia. So if you put it in an oscillator, like a torsional oscillator, and you cool below the transition temperature, it's like a whole bunch of your mass all of a sudden disappears out of your oscillator. And this is still like the standard tests that people do for these macroscopic quantum states. So it applies, it's because of the zero momentum issue, the zero momentum state. And it also applies in other interacting cases. And then superconductivity is just another manifestation of this in some sense. Again, it's interacting, so interactions are very important. But if the electrons in your solid can somehow condense into a state that has no momentum, then those electrons can flow without resistance in the electronic language. So how does that happen for fermions? Because fermions, this doesn't exist, right? You have one particle in that state, or two. Right, so this is the central mystery of superconductivity, is somehow those two electrons pair together, basically canceling their Fermi statistics, and that paired object can both condense. That's like the simplest, conceptual picture of what a superconductor is. And so in conventional superconductors, there's some pairing mechanism that happens between a coupling of the electrons and the phonons in the lattice, which is somehow kind of subtle. But you can basically work it out in some sort of perturbation theory. And for strong interacting type 2 superconductors, what we call high temperature superconductors, the essence of that pairing mechanism is still unknown. It's still theoretically unknown. And the problem with those cases is, if your interactions are too strong, then you can't do anything like this. You have some very theoretically complicated quantum many-body problem, and that we dedicated like 25 years of CPU time to, and still haven't solved that problem. And so there's a Nobel Prize in waiting. If the pairing mechanism for these high-temperature superconductors can ever be elucidated, which basically just explains why they would condense into a superfluid, if you will, a superconductor, then that'll sort of revolutionize condensed matter physics. And we're a long ways away from that, I believe.
Can I ask a very basic question?
I love it.
Because, let's assume this also works for linear dispersion. Then could
Uh-huh.
you have some sort of chain of condensation? Because this sort of breaks you want to measure, right? So you have some Goldstone modes which are linear dispersed.
Yeah,
Could
that's
you
right.
condense them? Have some sort of chain of condensation?
So if you have a linear dispersion, yeah, it's a good question. I don't know. I don't know if it's crazy or not. Maybe Xiaogun would know.
Could you explain what the question means?
So if you had a different dispersion, I guess, would you have different properties of your, I don't quite know how to say it. So one point is if you have, we're in a state where we don't have a well-defined particle number. Okay, so this is different than when we were talking about second quantization for phonons or something like that. So what happens is particles fluctuate in and out of the state depending on that distribution. Okay, so that's actually fundamentally different. And that in some senses depends on having that k squared. So in the case where we're talking about phonons and so on, you don't have a Bose-Einstein condensate because you're creating particles out of that vacuum. So that zero vacuum state, somehow is a zero particle state. So there's no particles that can actually Bose condense there. So I don't know. I'm getting off on a tangent, but I don't really know the answer, basically. So you mentioned something that it was, this, broken gauge symmetry. There's a Goldstone mode. So what does all this mean? I mean, I can explain this maybe very briefly. So one conceptual thing. Oh, before I get to that, so one conceptual thing which I think is important is the fact that, okay, this TC or this, this K, this momentum, I can relate the density to the de Broglie wavelength through that. And I can essentially just, invert that in terms of which equation do I want to use? Maybe TC. So in terms of the de Broglie wavelength, which is just h over p, I can solve for a lambda by just setting my kBt to p squared over 2m. This is just a rough, I'm just roughly setting my temperature to a value that is equal to my momentum there. And then I can solve that equation for t to get something that's, an order of magnitude 1 times the density to the minus 1/3. And remember, the de Broglie wavelength is somehow the spatial extent of the wave function. So this is another like condition for having a Bose-Einstein condensate. It's when your wave function or your wavelength is similar to the interparticle spacing. Remember, this is a three-dimensional integral, so that's why I have a 1 minus 1/3 here. So the picture is somehow that I have all these particles, all these bosons, and they have a de Broglie wavelength. I don't know. And that wavelength somehow becomes appreciable in terms of the interparticle spacing. And then this overlap of the wave function is what gives you this Bose-Einstein condensate. Okay, so it's just kind of a nice intuitive picture. So another thing, okay, so like I mentioned before, the number of particles in this state fluctuates. So that fluctuation means that I don't have this particle number basis, right? A BC isn't described, the ground state isn't described by the number of particles in it because its number can fluctuate. So what it is described by is an expectation value of a creation or annihilation operator. And these are bosonic, so they obey a commutation relation. So that's for particles in the ground state. And the expectation value of A dagger is just the number of particles in that lowest energy state. Okay, so because one of these is a Hermitian conjugate of the other, as you know, this implies that I can just write these as square root of the number of particles in the condensate. Just some very hand-waving sort of argument for the expectation value of A dagger A. You don't like it?
What does that mean?
That's just like these are the Hermitian conjugate of each other. So their expectation value is n naught. So I've just written them each as square root of n. When I multiply them together, I get n naught. It's nothing sophisticated.
Doesn't that brutalize your commutation relation?
Does it? So what's the inconsistency between these things here? No, my commutation relation, is, I can imagine these are root v here. This is 1 over the volume, something like that. So there's some inconsistency in dealing with translating between this number space and this, particle number expectation value. And you're going to actually look at this, I think, in your tutorial. But the point is that here, if I have a phase associated with this, I can still say this has a phase associated with it as long as these are the Hermitian conjugate of each other.
So
You guys don't like this,
n
eh?
just a number?
N is just the number of particles in the condensate. A naught is just the operator that raises and lowers particles into and out of your condensate.
But then don't they commute?
Pardon? Well, they're bosonic. It's a bosonic operator,
Yeah,
right?
but if n is just if we're defining A and A dagger as numbers.
Yeah, so this is saying there's some inconsistency here.
I think the more precise statement is that the vacuum expectation value of a dagger is square root of that.
The vacuum expectation value. Oh, yeah, this is
No, I mean that's right, but
the vacuum expectation value of A dagger is square root of n. Oh, yeah, I didn't write an expectation value here. Oh, sorry.
as you break the U1 global symmetry.
Yeah. Sorry, guys, I just forgot the expectation value. So the U1 symmetry is broken by this phase here. Okay, this phase is arbitrary. Okay, I totally confused you here. But all I wanted to do is introduce this phase and say that this phase is the broken symmetry in the problem. Okay? So this phase can be arbitrary, but it's this phase that is, it's essentially, the direction that the phase is pointing in space. It's a two-component vector, if you will. It's just the angle is what parameterizes it. And so this is the broken U1 gauge symmetry here. That's all I wanted to say. I didn't say it very well. You will explore this afternoon. So all superconductors, superfluids, Bose-Einstein condensates, the idea is that the expectation value of this A naught in the condensate has this broken U1 gauge symmetry, which is exactly the phase of the wave function. Then the order parameter just becomes, the order parameter of, or the expectation value of the wave function itself. You don't need a minus there. So it's just e to the I phi. So these things have a two-component order parameter.
So your Hamiltonian is this second quantized
Yeah, non-interacting. Yeah.
How can I see that it is actually gauge invariant?
This
is just a hand-wavy argument of how the expectation values of the operators
Yeah.
behave, but that doesn't mean that the operators or the A dagger A is a gauge invariant.
So you apply a number operator, and that's your gauge invariance there. So your phase should be somehow, pick up it should be invariant under application of this number operator. So,
It's kind of weird because it's like you're trying to look to the broken gauge invariance by just imposing that the operators had to transform in a certain way.
Yeah.
But why?
Why?
If you have a broken gauge invariance in this case, why saying the condensation of particles in the ground state is a signal of broken gauge invariance?
Well, are you saying why is this expectation value a signal of broken gauge invariance?
No, I understand that. Yeah, but it's somehow the argument that you're giving here is like, okay, let me write this expectation value in terms of this complex space, right? This space.
Sure, yeah.
Which you can do, but then claiming that you have broken gauge invariance is a different thing.
Yeah, so this, I mean, I'm just telling you, I mean, this isn't the proper treatment of this, obviously. But, so I think to look at broken gauge invariance, you really have to look at a Landau theory of superconductivity or superfluidity to see explicitly that that U1 is broken. So, but there's maybe an analogy. So this is essentially an XY magnet. So you could also rewrite this Hamiltonian in terms of a U1 invariant magnetic model. Okay, imagine that. So U1 just means it's XY symmetry. Okay, so the high temperature, the high symmetry phase, it means you're going to apply an arbitrary rotation to that any of those operators. And as you cool down into the ground state at 0 temperature, because of Merman-Wagner theorem, all of those magnetic, those XY degrees of freedom break and point in one direction, either X or Y or Z or something like that. Okay, that's the same thing. So the broken U1 gauge symmetry is just a broken XY symmetry. And that's the same Hamiltonian as like an XY model in some sense.
One other thing, when you write, you're saying that the order parameter is now your wave function.
Right.
Right? That wave function is a many-body wave function for the ground state.
Right.
So
but the phase is long, so it's a long-range phase coherent. So that phase, even though it's a many-body wave function, in the end, the order parameter is out of a one-particle phase. There's a single phase in the ground state. That theta, whatever it is.
However, if I'm over the critical temperature,
right, then
the
there's
wave function should be 0.
Yeah, so you lose that phase coherence. That's what the critical temperature is. It's hard to explain it. I'm sorry I didn't do any math. But I mean, this is the basic concept.
I mean, I want to understand this because I know if it's a condensate, the ground state then is the tensor product of the same, basically the same wave function, right? Every state is in the same wave function, so to speak.
Yeah. And those wave functions all have a single phase. So the phase of the wave functions all point in the same direction, if you will.
However, if I go over the critical temperature, the wave function is 0 or is something completely different?
Well, I mean, the wave function just becomes localized, onto each site somehow. So yeah, everyone has, every particle becomes its own particle again. It loses phase coherence across the system. So the order parameter is no longer, this macroscopic phase or whatever.
Is the fact that there's this phase coherence, is that implying that the creation and annihilation operators are now the same at all lattice sites?
Same at all lattice sites. So they're the Hermitian conjugate of each other. Like the operators are the Hermitian conjugate, but the expectation value is just root n naught, basically.
I mean, so each creation operator is defined at a particular lattice site? So when we go below critical temperature, it's the same operator each one?
Oh, well, this is a k-space. I mean, this is a sort of a k-space argument. Yeah, so these are k equals 0 creation annihilation operators. So it's the modes that you're like, it's the excited states that you're. It's not like the non-interacting crystal case or the Einstein crystal. It's the one where it's the modes that were exciting.
So how then would these expectations change above the critical temperature?
Above the what?
Above the critical temperature.
The critical temperature? Okay, so then it just becomes sort of a conventional, I mean, above the critical temperature, then you're just exciting modes in this excitation spectrum somehow here. And those don't have a definite number. There's no number, the wave function isn't described by the number of particles because there's particle number fluctuations there. So I'm trying to avoid introducing coherent states. I don't know, have you guys seen these things before? Okay, so it's, the ground state's a coherent state. This is the expectation value. But I don't know if Dennis will be talking about this in the tutorial today. I just wanted to sort of mention this to warm you guys up for what you were doing this afternoon. But I see I've just confused you. So Dennis, you'll do, all right. This is today, excitation spectrum, weak interacting Bose gas. So you're basically going to add a term to that Hamiltonian and work through all of this, right? Yeah, so maybe we'll save the questions for then. Yeah, sorry. But I think the only thing to take away is, the most important thing to take away is this picture here, the fact that a condensate exists, okay? The fact that it has something to do with the wavelengths interfering on the lattice length scale, okay? And some idea that we have a broken gauge symmetry that has to do with the phase of the wave function. And you look at, I think you'll look at most of the other details of this afternoon. So I think maybe it's a good tutorial in that sense, because I think there's a lot of conceptual sort of snags that you can run into with this Bose-Einstein condensate. That's just my way of avoiding answering any more questions, because I only have a day and a half left to teach you guys magnons and non-interacting electrons. So my goal is to prepare you for Xiaogun, who starts teaching you Monday. So before I start preparing you for Xiaogun, there's one other bosonic system I want to talk about. Okay? So we've talked about phonons. We've talked about the Bose-Einstein condensate, which is in some sense applicable to real particles. But I want to talk about another emergent particle that's analogous to a phonon. Okay? And that occurs in magnetic systems. That's when you have magnetic degrees of freedom. So this is to help you on your homework. Although I see I probably won't get to the actual quantum mechanical description today, but a spin wave is an excitation in a magnetic system in the same way that a sound wave is an excitation in like our lattice, vibrating lattice system. So imagine I have a lattice now, and that lattice has degrees of freedom sitting on it that are magnetic moments. Okay, and those moments in a low temperature phase can break some symmetry. Okay, so just like Anton Burkhoff taught you, you have a spontaneously broken symmetry in the ground state of the Ising model, say. Okay? And at 0 temperatures, that state is extremely boring. But let me tweak the Hamiltonian a bit to allow for a non-trivial excitation to come out of this. So this is broken time reversal. Broken time reversal. This is some SZ direction. So this is Z. So let's examine the low temperature excitations. Out of the state. Under the following Hamiltonian. So my Hamiltonian is going to be not the Ising model, but it's going to be the so-called Heisenberg model. And I'll just write it like that. So that's a classical Heisenberg model. So these are, if you want O3 spins, they have an X, Y, and Z component. Okay? And in dimensions greater than 2, these things realize a ferromagnetic ground state that is the same broken symmetry as the Ising model, but it has, there's an important, I guess, difference in the way the symmetry is broken that leads to low temperature excitations, which are gapless. So to consider the excitations out of this state, let's do a simple calculation like we did for phonons or for lattice vibrations in 1 dimension. Now, so if you haven't seen this before, this is nearest neighbor. It just angle bracket ij, si dot sj. So in 1 dimension, This Hamiltonian could also just be written indexed by I, and then it'd be I plus 1. Up to some factor. There's one bond per site, but I'll just ignore that factor. So my Hamiltonian is just a sum of SI dot SI plus 1. And I want to write an equation of motion for this in the same way that I used F equals ma to write the equation of motion for excitations in the lattice system. So now these are sitting on a lattice. But the lattice itself I'm going to consider frozen. So there's no phonons in the system. And I want to look at the excitations out of this ground state in the degrees of freedom interacting with this Hamiltonian. So before I start, let me rewrite the interaction in terms of an effective field. So you guys had mean field theory. So in the same spirit of that, let's consider an effective field here. Okay, inside an effective field is just going to be for site J. It's J dot, it's two neighbors, right? It's going to be J minus 1. So it's like if I have a site J and a magnetic moment on that site, because this Hamiltonian is only nearest neighbor interacting, this field only depends on the spin state at J minus 1 and J plus 1. So the nice thing about writing this as an effective field is I know how to write the equations of motion now. Right? So in the classical case when we're dealing with phonons, the equation of motion was F equals ma. Here it's just, I can just use the definition of the torque. The time derivative of the angular momentum, if you will, which is just a spin, is equal to the torque. So again, I'm going to basically calculate the dispersion, if you will, in the classical model with the classical equations of motion, and then look at how these are modified under quantum mechanics. So that I'll just write the classical equations of motion like that, S cross H. And for a single spin, as you know, these classical equations of motion lead to a precession around the direction of H. Well, more precisely around the direction of H. And this precession, conceptually, is what leads to the spin wave excitations. Okay, so for example, for a single spin, let's choose my magnetic field, H, in the Z direction. And then just looking at that cross product, Sx and Sy, the time derivatives just depend on the magnitude. I think that's the right minus sign. And what I can do is I can basically solve this equation of motion by looking at the spin raising operator. Okay. So quantum mechanically, it'll be an operator. Here it's just a linear combination. Sorry. So something like that. Then I can write for a single spin, I can write my classical equation of motion in terms of this linear combination. And I'll use this notation omega L, which is just the argument of the exponential that results. And it's called the Larmor frequency. And here it's just, of course, h. Okay, so this is all just the classical equations of motion. So the point is that if my magnetic field has a direction, then my spin, my magnetic moment, S, precesses around that h, the axis that defines h, right, with that frequency omega L. So now what I want to do is take a single particle equation of motion, just like we did for the lattice vibrations for phonons, and I want to look at the many particle case, say many magnetic moments, and you can see what I'm going to get out is that there's going to be a coupling between all of these S. So it's going to be modified quite a bit from the single spin case. So now let's consider the Heisenberg spin chain. So I'm just going to solve this in 1D again. And here my time derivative is just S at J cross H, where now I'm going to use my effective field for H. So what is it? J Sj minus 1 plus Sj plus 1. And what I need to do is take those cross products to write down the equation of motion. So to simplify the problem, I'm going to assume that basically the direction of the spin is mostly along the SZ direction, okay? And so, any x or y components are small deviations from this x direction. And this is basically the same assumption that you're using in your assignment that was given out yesterday, is that somehow the deviations from SZ are small. So what that allows us to do is basically we can write these cross products out and then throw away terms that are higher order in SY and SX, right? So we can just keep first order terms here. Okay, so we're only going to keep those first order terms in x and y. Okay, so this is quite nice in the end. So I'll get equations of motion. Okay, I'll just define an omega naught here. These are the first order terms. So x is yy minus y. And y is x, j minus 1, j plus 1, minus 2, j sj. Okay, so that's just keeping the first order terms. So it allows us to linearize those equations. And now I can define basically my S plus in the same way. And write this as a single equation of motion. And, oh, I forgot to find omega naught. Of course, just JS. Okay, and so this is my set of equations that I need to solve. This is one of them, right? It's the equation of motion for particle J, but see, it couples to its neighbors, J plus 1, J minus 1. Okay, so that's exactly, well, almost exactly the same as the lattice vibration case. It's like the same equation pretty much. There is one important difference. But unlike the single particle case, you know, these equations aren't decoupled in real space, and so we have to decouple them in K space. Okay? And again, that decoupling gives me a set of uncoupled equations in K space in this nice situation where I just have nearest neighbor interactions, right? So it's all entirely analogous to what we did in the lattice vibration case. The operator, or the objects look different somehow. I've kind of like alluded to the fact that we can add some quantum mechanics soon, but basically this is the same type of classical equation. There is some important difference out front here. It's not F equals ma anymore. So a is the second derivative of time, but otherwise this part kind of looks the same. So let's see what that leads to. I'll put exclamation points because I know you love this. So all we're doing is postulating a solution, essentially, that's S of j, let's see, t, is some coefficient, e to the I, you know, I'll write it like this, k position minus, I guess, omega k t. Okay, that's the same thing I did. I think I was calling him u's before. And then I just insert that solution into the equation of motion, and I'll get a set of equations that are decoupled in k-space. And you'll get a solution if, okay, that k-dependent frequency is equal to something. It's going to be 2 omega naught 1 minus cosine Ka. Well, I just have I've set a equals to 1, but I just put my lattice spacing back in there so it looks the same. So it's very, very similar to what we saw in the case of lattice vibrations, but it's essentially because, because we have a single derivative in the equation of motion here, I only have omega here, like 1 power of omega, and not 2 powers here. And so when you expand this cosine out for small k, right? So if I take, this is the dispersion. So if I expand for, if I consider small, k, I expand that cosine out. Whatever, you don't need to see me expand a cosine. Then this omega k will become proportional to k squared, because the 1's cancel, right? So magnons give quadratic dispersion, whereas phonons gave a linear dispersion for small k. That has to affect all the thermodynamic properties. So if we're measuring contributions to heat transport, like the specific heat as a function of temperature, for magnons, basically we have to get some effect from this k squared. And again, this all comes from the fact that the equation of motion comes from this torque equation, right? Everything else is the same, pretty much the same. The normal mode analysis, everything's decomposed in the same way. Oh, and if you're in 3 dimensions, I should mention too, all you have to worry about is, k dot the unit vector associated with all the directions there. So that comes out of the details of the Fourier transform. So I can calculate all the thermodynamic properties associated with this dispersion relation. But instead, let's look at what would happen quantum mechanically. So quantum mechanically now, my spins are operators. I mean, this calculation is good for giving us some intuition, but what we have to do is essentially worry about the spin value. Do I have a spin 1/2, like an electronic spin? Do I have some higher spin object? So this can become quite complicated. So those operators have all the usual properties. Most importantly, if I take the dot product of 2 operators and operate on a spin state, remember I get s times s plus 1, that spin state back. And I'm raising and lowering operators, which I use this notation already here, so I don't have to write all that down. So I want to assume again that I have spins mostly aligned in the x direction, sorry, the z direction, And now I want to consider small deviations away from that direction. And because we have operators, we expect the same type of quantization that occurred for lattice phonons, right? Whereas the phonons described excitations out of the, the vacuum state, single particle excitations, I can also expect a bosonic operator here that describes, deviations of the spin from the z direction. Okay.
Why is that a bosonic operator?
Well, the spins are the commutation relation of the spins. It's it's bosonic in that sense. So we can introduce a bosonic operator. That's okay. That's what you're doing in your assignment, right? We can introduce a bosonic operator. I'm just going to use the same notation as your assignment. That gives back the proper commutation relations of the spin, right? That's what I mean to say. And those bosonic operators are a number operator, which counts the deviation of that spin from being purely Sz. Okay, so I'm using the same notation as Dennis here. And hopefully this is right. There's my A. I'll write a hat now so I don't confuse it with an expectation value. And then I have an S minus A dagger I. Okay, so is that correct? Right, so expand to lowest order. Okay, so assume, say, a large S. Expand these things out. And calculate the commutation relation of, A dagger A and S plus S minus. And you'll get the proper spin commutation for one because you have the expectation value of Sz right under here. Okay?
Just one question. I know that this type of transformation preserves the commutation relations, right?
Mm-hmm.
But I just want to understand the physics behind it. We're considering the excitations to be deviations with respect to the original direction of magnetization. But
right here, yeah.
But why should I expect that excitation behaves as a boson?
Well, because if you assume it behaves like a boson and you construct this boson, it actually is the one that satisfies the commutation relations of the spin. So you can also construct a fermionic excitation. But how would you construct a fermionic excitation that obeys the original commutation relations? So that's actually, it's not a dumb question because it's actually, this is the concept of fractionalization is when this comes out. So if I imagine I have a bosonic operator that's somehow made up of two fermionic operators, and those fermionic operators are not necessarily confined in the sense that you guys learn confinement, then I can actually get emergent fermionic operators in systems like this. Okay? So what I've done here is somehow the simplest case, but the case that you're talking about it's not crazy. It actually, we believe it actually happens in some exotic systems. But in the end, the commutation relations of the underlying spin manifold have to be somehow obeyed by the transformation. Okay. So these fermionic excitations, some people would call these spin-ons. Again, it's just another, it's another way of parameterizing your spin operators with different types of raising and lowering operators. But that's, I think, much more complicated in principle. So we'll stick with these, which are your Holstein-Primakov, or HP, as they're now called, Holstein-Primakov bosons. And again, just do that exercise. Look at the commutation relations that you expect for S plus and S minus, and see that they obey the basic commutation relations. And again, the number of bosons Ni gives the deviation from the deviation of the spin from the z direction. So in your assignment, you're taking these Holstein-Primakov bosons, and you're going to expand them to lowest order. So lowest order describes non-interacting bosons. These bosons are called magnons or spin waves. So you can have interacting and non-interacting bosonic, emergent Hamiltonian, if you will. And the simplest one to solve, of course, is the non-interacting case. So let's do that. I'm going to solve the ferromagnetic Hamiltonian in the linear spin wave theory, which means I'm just keeping the lowest order term in that square root. So the normal mode is like a running wave of spin deviations. You can imagine the angle between these yellows in some long wavelength limit, and that's basically your classical analogy to what's going to go on here. So to linear approximation, well, first, of course, we have to define operators in K space. You're going to do all of this yourself, so I don't have to do anything. Sweet. Oh, I forgot my sum here. Sum over J. Sum over J. E to minus I. K dot R. J. What did I miss? A dagger. Take your Fourier transform. And then write your raising and lowering operators in Fourier space to lowest order in that Holstein-Primakov expansion. And then from this, you can rewrite your Hamiltonian. And that's all you're doing on your assignment. So these are operators. That's just an operator. So I have an S plus operator, right? I have an S minus operator. I don't know if I'm doing your homework for you again, if this is on that sheet, but the hard part is doing the Fourier transform. I should say the most rewarding part is actually doing the Fourier transform. And SZ, you need the Z operator too, right? So that's just S minus the number operator. So 1 over N. So you can label this K and Q if you want. Okay, so I've thrown out all those higher order terms that you would get from expanding the square root. What's wrong with this for spin 1/2? S equals 1/2. No, wait.
You can show that, but
I just meant the big S if the spin value itself is 1/2.
you're saying that SI is A and this plus is A and this minus is A dagger. So you're trading fermionic operator by bosonic operator to not that.
No, I don't think there's a problem. I don't think that's. You saying the commutation relation changes?
If you calculate the linear order, the commutation relation between A and A dagger,
Oh, yeah.
it will be
Wow.
1 minus 1 over S, blah, blah, blah. Right?
I was thinking of a more pedestrian problem. The fact that, how can I expand a square root when my S is 1/2? But, yeah, okay, so in linear approximation, to lowest approximation with S 1/2, you have to be careful with that. But in the end, it doesn't matter. Work it out for 1/2. It's actually, you know, the spin wave approximation for spin 1/2 ends up working actually quite well. Some other mystery associated with these Holstein-Primakov bosons, as far as I'm concerned. But for us, just let's just go ahead with leaving S in there. And all I want to do is rewrite the Hamiltonian. And the Hamiltonian I'm going to consider is the analogy to this Hamiltonian. Which is the Heisenberg ferromagnet. Oh, and I'll do it in 1D, I guess. So S. Well, I can either do J plus 1, or I can like sum over, you know, lattice directions. Or I can write as nearest neighbor. That's what I like. Let's do nearest neighbor. And ferromagnetic means you have a minus sign out front here, and then this thing's positive. So just like on your assignment, all you have to do is substitute in these operators. Okay? And if you're lucky, you should be able to calculate the dispersion. And I'm just going to write down what you get. You'll get, so in 3D, Z's my coordination number. So I'm talking simple cubic. Okay, so this is coordination here. Okay, so it's just like 1, 2, or 3, or 2 times 1, 2, or 3 for a simple cubic. And the most important part of the calculation is this thing I've called gamma. So for simple cubic, it's just the sum over all unit vectors, e to the I, k dot the unit vector. And that turns into a cosine. So you got to use some lattice inversion symmetry to get that. You know, plus z or minus z, plus x or minus x. Okay, so in the end, your Hamiltonian is, you know, precisely that of the previous Hamiltonian for phonons. So there's some modes, but I'll just leave those out. So I'm labeling by these Ks. with a dispersion that's, we're going to talk about next time in class, which is exactly this thing here, sum over lattice directions cosine k dot delta. So in the ferromagnetic case, you're lucky. Your Hamiltonian, after you transform it, has the same form as the Hamiltonian. You know, it's already diagonal in the number operator. Okay. On your assignment, of course you're not going to be that lucky. So for the antiferromagnetic case, this isn't true, and you have to diagonalize the resulting Hamiltonian. Okay. So that's the Bogolubov bosons that you're going to see in your assignment. The Bogolubov transformation will diagonalize the Hamiltonian that you see in the case of the antiferromagnet. So the quantum antiferromagnet when you have a plus sign there. So hopefully that's enough to give your assignment a shot. So what you'll notice here is you have the same dispersion relation as you did classically. You have some classical part, you have some equilibrium part, and then you can expand this cosine. So you're going to have a k-squared dispersion relation. It's the same as we had for the classical case. And so next class, I just want to explore a little bit of the thermodynamics of this dispersion relation. And then at the end of next class, we're going to talk a little bit about fermions, just to warm you guys up for what's coming in the next 2 weeks. Question?
Just to revisit my crazy question and connect the first and second part of this lecture.
Yep.
So you start with the ferromagnet, you break rotation symmetry, and you get the spin waves as Goldstone modes, right?
Yeah.
And they have dispersion k-squared.
Mm-hmm.
And by the first part of the lecture, that means they can both condense. Right?
But the ground state of, so these things exist in a well-defined Fock state, if you will, a particle number state. So in the zero number state, there's no particles in that state. That's what I would say. So whereas the Bose-Einstein condensate, which I didn't mention because I tried to do it in 3 lines, it's not a Fock state, right? It's not a particle number state. It's a coherent state, which I didn't talk about. So somehow that's the main difference. Okay, so we'll talk about this. Again, we'll talk about excitations out of this vacuum state and the thermodynamic consequences tomorrow. Other questions? All right, see you guys then.